grateful to the committee that decided to invite me here, so it's a great pleasure to talk at this conference. And I'm trying to guide you in the journal today in a domain which is very different from that explored by Claudia Sagasti-Zabal in the previous talk. And this is joint work with Coralia Curtis from Oxford University and Nick Gould from Rutherford Appleton Laboratory. And these are the thanks for the various organizations that have supporting us for what is a stream of work which lasted for the last 5 or 6 years. So we will consider the problem of nonlinear optimization here, and I will nowhere make assumptions of convexity. So I'm trying to look at the problem without convexity assumptions, and that will create some difficulties as you might anticipate. The most basic problem of nonlinear optimization is obviously minimizing a non-constrained objective function f of x. And we assume here that it is smooth. And this is the first difference with Claudia's talks. Here, everything will be as smooth as needed. And we will see that it might be sometimes a lot. We also look at a very important special case, because this has been the subject of many talks in this conference, the nonlinear least square problem, which happens, for instance, since it's the flavor of the day, in deep learning and other subjects related to artificial intelligence. Okay, so this is a slide which my friend Andreas sitting there will like very much, because it's an observation of his. In 1981, if you assume that you can write the Taylor series of order 2 of this function f, and if you assume that f has a gradient and has a globally Lipschitz continuous Hessian h with constant to L, then this first equality here is nothing but the Taylor series with integral remainder. This is elementary analysis. Everybody remembers that formula, and the next inequality is just using the Lipschitz constant for bonding the difference between those two Hessians here. Well, that's all nice, but the nice observation by Andreas, I think, is that it can be used as a tool for optimization directly. If you look at this function f of xs, this is the function we want to minimize. We want to find an s which makes the function smaller. And as a consequence, if we make this model of s here smaller, it is an overestimate on the true function, and so we will decrease our true function as well. Okay, so this is, we can in fact minimize this function as a function of s, and then this will give us an overestimate of our function f of x. Okay, the trouble, of course, is that the Lipschitz constant is usually not known, and so we may replace it by some adaptive parameter sigma k, and in fact look at a model of the objective function, which is like this, which is the Taylor series of order 2 plus a regularization of third order. This is a second difference with Claudia's talk. In Claudia's talk, we had regularization of second order, and these were the Prox function, and the regularization of second order are well suited to first order optimality measures, like the gradient, but not so much, in my view, to second order models, like this one here. So we have, in fact, a function which is cubic in S. Can we minimize this? Yes, we can at least find an approximate stationary point. And what we will look for this approximation is to find a point whose gradient, that is the gradient of the model, is small compared to S. That is something like this rule over here. Notice that there is no global optimization of the cubic model involved at all. We only need an approximate first order critical point, nothing more. Okay, so that gives a regularization algorithm, which is like this. If you start from somewhere with some regularization parameter, and then if the gradient is small, you terminate. Otherwise, you compute a step by minimizing this cubic model I just told you about, such that it decreases, which is the least you can ask, and also such that the gradient is sufficiently small in the measure I discussed on the previous slide. And then what you do that, you have a step, you compute the reduction which is achieved by this step compared to the reduction which is predicted by the Taylor series. And then if this is a positive number, say larger than 0.1, then you accept this step, otherwise you don't move, and you restrict you increase the regularization parameter sigma, because if that happens, it means that your model was not an overestimate of your true function. And if it's not an overestimate, it must be because the regularization parameter is too small. So we just increase the regularization parameter and do it again. This is essentially what happens here. Okay, so that's a very, very simple method. There are quite a number of interesting things about this method. If you look at the model with the exact Lipschitz constant here, Nesterov and Polyak shown that you can minimize this cubic model globally, and in fact even Andreas also showed it in his 81 paper. And exactly, you can even do that essentially to accuracy of your computer, at least if factorization are available, or if there is a sparse factor scheme. This function M can be violently non-convex. This is quite noticeable. This is quite far from a convex function. You can prove rapid second-order convergence to second-order critical point, like Newton's method would have. But we will see that we are not so much interested in that. We are more interested in the third point here, which is this method has a better worst-case function evaluation complexity than was previously known. So what is that? I will come to that in the next slide. But there are obvious questions at this stage. Can we avoid the global Lipschitz constant? The answer is yes. Can we approximately minimize M at variance with this and retain the good worst-case analysis? The answer is again yes. And does this work well in practice? The answer is a smaller yes, but I won't have time to discuss, but it's nevertheless a yes. Okay, so what is evaluation complexity? Evaluation complexity is trying to get a global rate of convergence, not a local rate like Claudia was discussing before, which happens asymptotically, and you may have to wait quite a long time before it actually occurs. But here we want a rate of convergence from iteration 1. That is, we want to know how long do I have to wait, in the worst case, for this termination criterion to happen. So if I apply this method, how many evaluations of my functions and its derivatives would I need to do before this will eventually occur? And this is the interesting bit here, is that it was shown essentially a la Nesterov and Polyak using arguments that are somewhat similar to them, well, actually not true, but we'll discuss them in a moment, that this complexity is 1 over epsilon to the 3 halves. And this is much better than anything else that was known before. And as a side result, we get also a complexity substantially worse for conversion to second-order critical point. That is, if you want to find a minimizer, not just a stationary point, then this is substantially worse. Because this result is so simple to prove, I will prove it to you. But I won't use Nesterov and Polyak's proof because it was using different assumptions and it's more complicated. This is the first result. The first two results here are essentially the straightforward consequences of the Lipschitz continuity assumptions. Right? If I have a Lipschitz continuous Hessian, this is true and this is true. This is just standard Taylor series expansion and bounding. There is absolutely no secret in that at all. And it's totally standard. There is nothing new in there. Lipschitz continuity gives you that. Second observation is that the function minus the model here is going, minus the Taylor series, is going to give at least that. And why is that? Simply because the model that we minimize is just the sum of these two things. Okay, so if we decrease the model, the difference between f and t will be at least that. So it's straightforward. Next point, you cannot increase sigma infinitely often. Intuitively, this is very clear. We know that if sigma is as large or larger than the global Lipschitz constant, it will be an overestimate of the function always. So as soon as it gets to this value, or within a fraction of that value, it stops increasing. Okay, so this is the formula to give it to you. I won't go into the details, but essentially it tells you exactly what I just said now. So it's not very long, and you see this proof is also short. The crucial point is here. And the crucial point is look at this. I want to compute the gradient now, not at the current iterate, but at the next iterate. And the gradient at the next iterate is the same as this gradient minus the gradient of the Taylor series, plus the gradient of the Taylor series, plus the sigma minus the sigma, right? So I get this bound here just by using triangle inequality, nothing fancy. This is, I know, this is bounded by this quantity because of the Lipschitz constant. This guy, I also know, this is the gradient of my model. So it's bounded by this, it is this guy over here. And this one is what it is. So I go to the next line. I get this term here. This is bounded because I've required this gradient to be sufficiently small. So this is bounded by this constant. And this is sigma over here. And sigma, remember, is bounded by sigma max. So what I have is that my step sk is larger than this quantity involving the square root of the next gradient, not the current gradient. Okay? And now it's finished nearly. You only compute f low is some lower bound on your function, f of x0 is the f at the starting point, and you say, all right, this thing is larger than the sum of the improvement I can guess over all the steps of my algorithm. Each improvement is, remember, I consider only the successful iteration, that is, these iterations for which the ratio of achieved to predicted reduction is larger than 0.1, okay? So this is 0.1 here, times larger than the sum of the predicted reductions. And each one of these predicted reductions is bounded by a 6 times the minimum of SQ. So we get this. And this is the cardinal of the set of iteration where this happens. And this SQ, we know that a square is larger than something, so if we replace that, we get this condition here. And this is the gradient at the next iteration, but this is, as long as we have not terminated, this thing is larger than epsilon, this gradient. So we get this quantity here. So what this means is that at every iteration, at every successful iteration, we get a function decrease which is at least that big, okay, up to a constant. And the result of that, now you can fiddle a little bit because not every iteration is successful, but you can show that the number of successful iterations, total number of iterations is bounded by the number of successful iterations. And so the result of that is that g of xk plus 1 must be smaller than epsilon after at most that many successful iterations. Okay, there we go, finished. We have proved the complexity result, and it's also the shortest convergence proof in nonlinear programming I'm aware of. There is no way to improve on the, at least I don't know about it. Okay, so is this bound sharp? And the answer is yes. And in fact, we can design a function in 1D, and this is going to be important, which oscillates very tightly, as you can vaguely see here. This is not simply that I was trembling like my pointer is, but The curve is really trembling here, and I'll show you the derivatives to show you it's definitely non-convex. This is the first derivative. This is the second derivative. And the interesting bit is that this is the third derivative. And why am I interested in the third derivative? Because I want it to be uniformly bounded to ensure that I have Lipschitz continuity of my Hessian. Okay? So this is a perfect example. It works exactly, it fits the theory exactly, and on this function, the method I described requires exactly epsilon minus 3/2 iteration. So you cannot improve on that. Okay, what about other methods? Well, it's been known for a while that the steepest descent method requires that many iterations, which is substantially worse. And in fact, is it sharp? Yes, we also show that it is the sharp. We cannot improve on that. The surprising thing here is that Newton's method requires also epsilon to the minus 2 iteration. And again, this is sharp. So I will contradict Claudia, at least in the worst case analysis. The fastest method for computing a solution of Newton of nonlinear equations or minimizing a function may not be Newton method. It may be a regularization method like this one. That's important. So this is the objective function for slow Newton method. It's zigzagging even more, but it can be defined, and the details are given in the paper if you're interested. You can get the details where you can show that on this method, Newton's method, will take as many iterations as steepest descent method in its worst case. So it means that it is really very slow. So that's the function for steepest descent. This is just to show that they all look the same. I don't want to go into the details, but they all look like zigzagging this descending method. Okay, well, you can get a bit more general than that, and you can ask yourself, can I look at second order methods in general? So what do I mean by a second order method? For me, a second order method is a method for which the step is computed by possibly approximately solving this equation here for some lambda bounded by this quantity. So it's a very general setting. It includes Newton, the regularization method I presented, Levenberg, Morris, and Nachwer, first trivial in most cases, the Curtis, Robinson, Samadi class, and the Royer and Wright class as well. So it includes just about every second method we know about, and more. But what we can show is that this method will require this ugly formula here when the Hessian here is no longer Lipschitz continuous, but Hölder continuous. So the result of that, we don't need to try to interpret it. The main thing is that it ranges between epsilon to the minus 2 to epsilon minus 3/2. So the result of this slide is that the regularization is optimal in terms of complexity within this class, this wide class of second order. There is no method that is better. And in fact, it's not the only one. The Curtis and Samadi and Royer and Wright methods are also optimal in that sense. Okay. So what happens now if we jump into the deep water, really? That is, if we look at models higher of degree 2. So if we look at the Taylor series of order P now, and write a regularization of order P plus 1, this is the Taylor series, nothing new for you. And now I'm requiring that my step satisfy this condition, which is the exact similar of what I had before. And now I get another method, which is exactly the same as before, except I have P instead of 2 before. Like this is really the same. Okay? So what can I say? I can prove that you can find a first order condition now after at most epsilon minus P plus 1 over P evaluations. So this goes slowly to epsilon minus 1, which is the complexity for convex problems. And it's also valid not only for unconstrained problems, but for convexly constrained problems. That is, problems whose constraints are convex. Moreover, if you can do something similar for second order, and this is a brand new result. This was published very recently. For second order, you get this order here. So if you take p equals 3, you take a third order model, and you want to find a second order point, what is the complexity? You find a complexity of epsilon minus 2 now. So this is substantially better than epsilon minus 3 that we had before. And it's quite natural. We obtain a reasonable order, a reasonable complexity for first order point using second order models. If you want to use a reasonable complexity for second order point, you should use third order models. And this is what it says. Okay, so you may think using high derivatives, does it make any sense? But there is at least one case where it does make sense, is for this class of partially separable functions, one of my old horses, and Andreas's too, is that if a large number of functions can be expressed as the sum of many functions, potentially, but each one of them depends on the low-rank term. And if you have that, then it's trivial to check that the derivatives are essentially very small, and the size of all this derivative tensor is typically much, much smaller than the size of the true tensor of the real function. So although it might be difficult to compute this thing, computing that guy is usually quite feasible. So I don't think one should give up hope of using higher order methods. So at this stage, we can ask the question. If one uses a model of degree p, why be satisfied with a first or a second order critical point? So, but what do we mean by a critical point of order larger than 2? And in fact, what are the necessary conditions that would apply for this critical point of higher order? It's not an obvious question at all. So first of all, we have to get realistic. You can't do everything. On this example, this is a function which was essentially defined by Peano and Hancock a long time ago. It's a very old example. You have this point here. The origin is a saddle point of this function. You see, it goes up in this direction and it goes down in this direction. So it's a saddle point. But along this line here, along the horizontal axis, because of this term, the Taylor series is identically zero. Everywhere, every term, as long as you can, as you want to make it. So if you approach this saddle point along this line here, there is no way to use the Taylor series to find it's not a local minima. So using Taylor series has its limits. We know that. So, and there is another interesting thing in this example, is that you can take any straight line passing through the origin, and along this straight line the function is convex. So it means that you cannot just look at lines to decide whether you're optimal. You have to look at curves. Because on this example, if you only look at lines, you would conclude that you are at a minimized. And that's not the case. Okay, so looking at optimality along line is not enough. And we can even find worse examples like this one, which was suggested by Avery and Lewis not so long ago. There is even no continuous descent path from zero, although it's not a local minimizer. So, okay, we have to limit our ambitions. So, the first thing we could do, all right, we cannot find a general descent path, but what about considering polynomial path at least? Just look at something simple to start. And so we consider polynomial path in this form, and then we want to say that it is still a necessary condition that the function does not increase along any feasible polynomial path. That's definitely a necessary condition. Okay, so if we replace this and manipulate this thing with a little bit of patience, one obtains these conditions here. Suppose that x star is a local minimizer, then this guy here is positive, and this is a logly index set here. For all s's, the s's here are essentially the components of this path, for all s's such that this is true. And this is pretty ugly, I would say. Interestingly, it reduces on standard inequalities on the gradient and the Hessian for all those 1 and 2. So it is a direct generalization of what we know for orders 1 and 2. But for higher order, it's complicated. It's still okay for all the 3 because it still involves looking at an inequality of the higher order tensor, that is in that case the tensor of order 3, in the null space of the previous tensor, which is in that case the Hessian. You want to have a positive curvature in the null space of the Hessian. That's okay for all the 3. But for all the 4, this is no longer the case. We have a mix of terms, and this thing becomes really very difficult. So is it desperate? Well, maybe not. So let's make another big assumption here. That for a small delta, we can find the global minimizer of this Taylor series in this small neighborhood of a current point. Okay? And let's define phi of x, phi of delta of x, be the decrease that we obtain from moving from x to the global minimizer in that small neighborhood. Okay? And then we can show that if you take the limit when delta goes to 0 of this thing here, if this thing goes to 0, then you recover the path-based necessary condition for high order optimality. So in that case, it means that this thing here could be a reasonable stopping rule or reasonable measure of accuracy for high order. Of course, you need to compute the global min in a small ball. This is not necessarily trivial, but at least it provides some measure of optimality. And in fact, you can show that if this measure of optimality satisfies this, then locally your function is essentially flat, or essentially a minimizer. And the radius of the ball where this happens increases with the degree. So that's a useful thing for global optimization, for instance. Okay, so at least we have an algorithm, a theoretical algorithm. We compute a step, we evaluate the gradient and this global minimizer measure here. If this is large, that is, we found a point where it decreases, but we just move to that point, and otherwise we terminate. And then, of course, we do the same game as before. We can compare the achieved to predicted reduction and move it as changed. And if it has not changed, we reduce the radius in which we want to look for this polynomial. Okay, and surprise, we can now show that if you can do this, you will need at most, epsilon to the minus q plus 1 evaluation of the function and its derivative to compute a qth order critical point using that technique. Okay? The same result also holds if you have convex constraints. They don't change the complexity at all, which is quite surprising because, for instance, the box is a convex constraint, and you may think it has a combinatorial nature, but it doesn't affect the complexity of the problem. Okay, so where do we stand? This is the order of the critical point. This is the degree of the model that we are looking at. What we know is that for first order points, that is stationary point, first order method will give you epsilon to the minus 2, so that's steeper descent. This is the first method I presented to you, which is the cubic regularization, and we have shown that these two are sharp. This is yes. And now if you continue along this way, I've shown to you, or I've mentioned to you that this can be generalized to this formula here. For second order critical point, we know at least for unconstrained problem that it generalizes to this formula. I don't know for the moment for convexity constrained problems. Along this diagonal here, you will find the result I just had on my previous slide, which is using this generalize the termination rule, and this gives you the whole diagonal here, but in here we really don't know what happens. So this is still open whether we can extend the result of the first lower rows here to the upper rows or not. Okay. I want to mention here a very, very recent paper. In fact, I got it about 2 weeks before coming here. And this is interesting because in the counterexamples I showed to you, we show that essentially for all epsilon and every n, there exists a function for which we have counterexamples, slow converging methods. The new result is of a different type. It says that for epsilon, there exists an n, that is, there exists a problem size for which any method based on Taylor expansion will take exactly the same number of iterations. So the trouble here is that in this n can be as large as the number of iterations that you require. So when you have a problem, you say you have a 3 or 4 or a 15-dimensional problem, well, you don't really know whether this applies because it may require a problem in the zillions of dimensions to be true. Okay, so this is an interesting result because it's general. It's for all orders, but it's weak in the sense that these quantifiers here are quite a bit different. But this is very new and it's just appeared on archive for those who are interested. Okay, so that was for the unconstrained case. So let's look at the equality constrained case now. Now we want to minimize this function subject to C of x equals 0. And x again in a convex set. So this is a general framework for nonlinear optimization. It covers everything. And now we are going to look at the Lagrangian of the problem, it's no surprise. And the Lagrangian of the problem is this guy here, and we are going to look at the Taylor's expansion of the Lagrangian. And if we do that, if x is a local minimum, then this thing must be true for all feasible paths such that they don't violate the constraints. Okay? So that's correct. So this is a case, and if you, I didn't write these equations in full detail, but it's even more horrible than the previous ones. So it's essentially even more hopeless because the constraint now depends on the components of the path, and this is really becoming complicated, the growing number of coefficients. And now it involves more than the higher order tensor, including for order 3. It's even more difficult than in the unconstrained case. So only the first 2 orders seem to be manageable. At least I want to give you an idea for a first order algorithm. It's a 2-phase algorithm. In the first phase, you try to get the constraint smaller than epsilon, by minimizing this function here in the convex set if necessary. Notice that we don't want to get this small, which would be the normal termination for this function, because that would, the difference between that and that is that we have to assume a uniform bound on the smallest single value of the Jacobian, and that's a very strong assumption. So we can get rid of that, fortunately, and it's possible to get this. Okay, so we can do that in a certain number of iterations, and then we want to track the trajectory by staying close to this trajectory and minimizing t, which is equal to an order x. Okay? And we do that by applying a method, and the method that we want to do is to minimize this penalty function here. That is, we try to minimize f subject to a penalty in C. Okay? So this is the algorithm. You apply the first stage, and you can show by using the theory I just explained to you before that this requires at most that many evaluations, where pi here depends on the order of complexity of the unconstrained method that you're using for solving the problem. So if you use a first order, pi is 2. If you use a second order, it's -3/2. Okay? So you can get this, not many evaluations, and you can do this in exactly the same number of evaluations. So as a result of that, we have that the algorithm take order. I need to qualify this a little bit, but essentially that's what it is. It takes that many evaluations to find an iterate such that it is an approximate saddle point of the Lagrangian, or it's an infeasible local minimizer of the history. So I want to get to touch here to a comment that was made by the presenter on the game theory the other day, Christophe Bocaridis, and what he says is that it was an open question to find minimax, the complexity of minimax for the non-convex case and non-convex case. At least that's one particular example where we know this is a minimax problem. The Lagrangian is a minimax problem, a specific one, I agree, but it is at least one case where we can compute the complexity bound for computing these particular points. Okay, so would it work if we were to increase the order? And the approach that I described to you for q equals 1, it really depends very strongly on the fact that the gradient of the Lagrangian here is a multiple of the gradient of this penalty function. Okay? And it's also true for q equal 2 because we have this. But then we have to, it's only true, this equality is only true in that null space here, in that subspace here. But that's essentially the subspace which is defined by the first order condition. So it essentially says that you have to have something which is positive definite in the null space of the constraint, so it's no surprise. It may not be impossible for q equals 3, because we again have this property here, which is always the same multiplier. But now the subspace here is more complicated set depending on all these derivatives. So it still may be possible to work out what that is. But the interesting thing is that it's really impossible for all the four. And why is it impossible? Because in this case, the fourth order derivative of the Lagrangian is the fourth order derivative of a penalty function plus a bunch of other terms. And the green terms are fine because they cancel out. But the red terms do not disappear. And I don't see any way to get rid of those red terms over here. As an important sequence is that every approach based on a quadratic or even more general penalty function is bound to fail for q large equals 4 or larger. So penalization method will only work for order 1, 2, and 3. Beyond that, I think we definitely have to invent something else. And this is quite a challenge because so far we don't know anything else, or nearly not. So I'm coming to my conclusions. I've presented you a complexity analysis for general qth order critical points. And I've shown to you that for the unconstrained and the convex constrained case, the complexity is given by this formula here, depending on the order of criticality that you look. But that you can also get the criticality, complexity measure for the constrained case using this formula. Finally, there are many other things to say. Florian Jara as an example showing that global optimization is much harder than this. Here we are interested in local optimization. So if you want to do global optimization, then the complexity bounds are essentially exponential. So it's much, much harder. And there are many questions remaining. What do we mean by high order optimality with high degree model? Is it practical? The first experiments using programs seem to indicate that it might be useful in some cases, especially when you want high precision and the dimension of your problem is not too large. But this might really be worthwhile. And can we get beyond first order results for the equality constraints? I don't know. So these are questions that remains to be seen, but essentially I want you to take away some messages here. The first is that evaluation complexity with the improves with the model's degree. that critical point of order higher than 2 are in general quite hard to find. Maybe 3, 4 is already requires global minimization, so it's a bit tough. Approximate critical point of high order can be defined, so it's not a trivial task to define approximate critical points of high order. And you can find an evaluation complexity bound for those if you assume that you can solve this little global optimization problem. And this holds for both unconstrained and convexly constrained problems. Can one improve the complexity bound for P larger than Q? So this is the sort of triangle I had in my slide where there were lots of question marks. I don't really know. What about high order criticality for equality constraint problem? And can be more practical? It's already a little bit. Can it be more practical? That's obviously an open question. Many thanks for your attention.
Thank you very much. Yes, it's working. So somebody wants to make a question? Yeah.
So I suppose you didn't assume linear independence because then everything would be trivial immediately, or?
No such thing, no.
What?
No, I didn't assume that. No.
Yeah. Then you could just eliminate and have the unconstrained case essentially. But the other thing is I'm wondering about terminology. I mean, it seems to me if something is a critical point of f, it should also be a critical point of minus f. I like to call this higher order minimality.
Well, that depends. For odd orders, I agree with you. For first order, it's okay. But for even orders, a minimizer is not a maximizer. You have to change sign at least somewhere.
Yes, but your notion of criticality is dependent on the... I mean, doesn't it say up to whatever you compute, it's a minimal point? Rather than a critical point?
No. It says first order is a critical point, second order is minimal point, third order is a minimum of the...
Well, I mean, it's necessary conditions for minimality, isn't it?
Yes.
That's what I mean.
Absolutely. This is what
and it's not necessary condition for maximality.
But you can look at minus the function and
But the terminology of the critical point of f doesn't say it's the same kind of critical point for minus f.
No, I agree, but it should be the same already with the min-max for a minimizer. You have to change the sign of your function somewhere to get the same condition.
Well, then another remark that I'm trying to figure out, you talked about partial separability.
Mm-hmm.
I think the machine learning people, if I learn that much about it, they call it the finite summation condition.
Well, I mean,
is that true or not?
No, I don't think it's true. I think there is a difference between the two conditions. What the machine learning people very often is they have a sum of many terms, but it's not in general true that each of these terms depends on the low rank version of the variables. So each term might depend on all the variables in an unspecified way. I think partially separable is stronger and therefore can be exploited more heavily because it says that each one of these functions only depends essentially on a few variables. And that's not the case in general for the machine learning.
But then every single term in all variables satisfies the finite summation condition.
Sorry, I don't quite get what you want to say.
Just one function in x1 through to xn.
Yes.
Yes. Satisfies the finite.
Absolutely, but they are not interested in that case. They're interested in case like say speech recognition, where you have this bunch of functions that all depend on your signal, but they depend. You look at spectral variation or different parts of the function, and so typically they have large sums, but these sums are each function in the sum is not so structured as we did invent in our paper in the 1980s. So that's a difference.
Somebody else?
I was wondering if some other problems could be treated also with the tools. For instance, the animation of global optima.
I don't really know. I'm not an expert enough in this area. These tools are essentially local. One has to remember they are based on Taylor series. So Taylor series are local. No, well, they give a rate of approximation which increases with the degree. So that might help because it provides underestimates or overestimates that are valid in larger domains, but they are not valid globally, that's for sure.
How about that? I mean, I think you can compare your approach.
Good question. I don't know.
Thank you for the wonderful talk, Philip. You mentioned high-order model, so I just wondering if you're using high-order model, how you're solving the subproblem.
Well, you can use any method you like. I mean, remember that if you want to get first-order points or even second-order points, all you need to find is approximate critical points of the same order for the model. So you could use this method too, one order lower. You can use anything you want. Now, in the theory, this doesn't impact the result. Why is that? Because when you estimate the model, you solve the model by any method you like. You never re-estimate the functions or its derivative. You only evaluate the model. And the model is computed derivatives already. Okay? So you never estimate new function value or new derivatives when you solve the model, even if it's complicated to solve it. And it might be rather complicated. And that's what we observed for some very difficult data fitting problem. Have in mind problems that are asked by physicists and chemists where they want high accuracy and they have very nonlinear models. And if you want to have reasonable approximation to very nonlinear models, quadratic won't do. Quadratic is not enough. You need to go to higher degree, and if you go to a higher degree, then you have to solve these higher order models. You never evaluate the true function, the sort of nasty thing that the chemist or the physicist gives to you, but it may still require some effort to solve some problem. But you need fewer iterations, that's clear.
Do you think high order will be improve complexity?
Yes, absolutely. Not for every type of model. I don't think this is a tool which you can apply to very, very large problems unless one has very specific structure like partial separability. But otherwise, yes, for a problem for which the size of these high derivatives is manageable, I think it's quite promising.
Is there any other question? No? Okay, so thank you very much, Philippe.